Thank you everyone for joining us on a Saturday. It's a great pleasure to introduce Dr. Kusala Rajendran to all of you. She's a renowned geophysicist with roots in Kerala. She did her graduation in chemistry before she became interested in geophysics and then subsequently did her PhD in seismology. She's worked on earthquakes in India with a focus on Himalayas and the Andaman and Nicobar Islands. Her work includes the 1993 Killari, 2001 Bhuj earthquakes and the 2004 tsunami. She worked as a scientist at the Center for Earth Science Studies at Trivandrum before moving to Indian Institute of Science in 2007. She has also co-authored 2 books with her husband and collaborator C.P. Rajendran, a textbook titled Earthquakes of the Indian Subcontinent and a popular book titled Rumbling Earth. She has published nearly over 100 research papers and she has received the first National Women Scientist Award in the year 2018. And with that, I welcome Dr. Kusala.
It's a pleasure to be here and talk to you about parts of my work. I've been working on earthquakes for about 4 decades now, so it is very patchy that whatever I can communicate in one hour, I can try to give you glimpses of my work. The organizers also wanted a highlight on the earthquakes in Karnataka, so I have not worked on the earthquakes in Karnataka, but I've just added a small patch to fill in that requirement. What you're actually seeing on the screen is the western India, Gujarat, actually the run of Kutch. Actually what you're seeing, the white color is a salt marsh, and the person in red, that is me. CP must be in front. So we were actually, in this place, the vehicles usually get stuck. We go here. I'll talk about this earthquake and why we are there. We came back from the US, trained, CP was particularly trained in looking at earthquakes beyond history. Earthquakes that happen now we know. Earthquakes in the history we know. But earthquakes that have happened beyond history is something that is of great interest to us, for which you need a lot of information, like a detective will work on information and find out logically what has happened. So there was an earthquake here in 1819. So that was a very big earthquake. It was mysterious because it produced a long fault, actually a scarp. It's like a dam. It actually produced a mound that runs into today's Pakistan. So that is 90 kilometers long, 60 in India and 30 in Pakistan. So when we got trained in this area of how to look at earthquakes beyond history, we wanted to go back to this place and look for the past earthquake. When was the past earthquake? So it was great difficulty we got in here because it is it's under BSF control. In the time we worked, that was in 1996. It was very difficult to work there because of the border issues and not much of facilities were there. But yet, I have worked in many places in India and abroad. But to me, the most fascinating, most challenging, but the most fascinating place is the run of Kutch. So that's why I'm very possessive about this. But at all the perils, like vehicles get stuck and we have to walk and all kind of problems are there. There's no place to sleep. We sleep in the bunker. So, but still it is the most challenging and most fascinating place where I worked. I'll come back to this little details. I've organized this talk with, there are 4 basic ideas. As one is many of you do not have much of idea about earthquakes and what is the magnitude, what is a fault. I guess, any of you have any thoughts about that, or all of you must be new to this whole thing, right? So I put together some of those things so that you can appreciate what we are actually trying to do. And then I will touch upon a few Indian earthquakes. I have worked on a lot of earthquakes in the Himalaya, run of Kutch, Narmada, Killari, Kerala, and also Andamans, in Northeast India. So I'm just touching upon a couple of important earthquakes and focusing more on the South India. And then I will talk a little bit about the earthquake history of Karnataka. And then I want to just highlight what is it that we know and what is it that we do not. Because every earthquake, every presentation about earthquake ends up in a question of, can you really predict an earthquake? And if you cannot, why is it that you cannot predict an earthquake? So I'll touch upon those issues. So the one that is on the extreme left is what is a seismograph. So what I was telling is earthquake is a release of energy. So elastic energy stored within the rocks is released, and that is what comes out as seismic waves. So the recorder is a earthquake recorder is a seismograph. What you see on the extreme left, and it produces a seismogram, which is nothing but the record of the seismic waves, which are the P waves, S waves, and then subsequent waves will come. So that is the way you actually understand an earthquake. So you can see that the P and S are timed. There's a difference in the time, and that time tells you where it started. And because we know the velocity of these waves, they can be modeled to find out where it started. And if you have many such seismograms, you can find out where exactly the earthquake actually occurred. Earthquake can be very damaging. Every time you hear about an earthquake, you always think about destruction to buildings, damaged, roads and things like that. So this picture on the right top is an image from Bhuj. Bhuj earthquake damaged many things, including as distant as Ahmedabad, 200 kilometers away from Bhuj. It damaged many buildings because of the nature of the soil. And another thing is with the tsunami. All till 2004, tsunami occurred in India. We never really worried much about tsunami. So that was our experience also as scientists, that tsunami has actually occurred. So tsunami is caused again by great earthquakes, which are happening on the ocean floor. So because we had a tsunami, I will touch upon that too. And here what you're seeing on this is what you call a fault. A fault is created by an earthquake, and once the fault is created, they get reactivated in subsequent earthquakes. A fault is nothing but a displacement which will be expressed in the geological sections, and some of them can be expressed on the surface. And finally, I'll come to the question of why is it so difficult to predict earthquakes. First of all, we start with an understanding that earthquake is not just a random thing. It has a pattern. It is not that it can just occur anywhere. It is not like that. What you are seeing is the global seismicity from 1904 to 2020. You can see that the red dots, which are the earthquakes, the blue ones are actually deeper ones. Earthquakes occur at different depths. Some of them could be like 10 kilometers, some of them could be 600 kilometers. So the blue ones are actually the deeper ones. And that's also where you will get all your volcanoes. So anyway, so what you are seeing is, the gray patches, which are the continents, you don't find many earthquakes happening within the continent. Like if you look at the African continent, if you look at the western part of Africa, eastern part of South America, Australia, eastern United States, you don't find earthquakes happening there. But right on the border, you will find they are all, it's all like a line of, you can define a line, which is nothing but the plate boundaries. I will talk about that. So fundamentally, earthquakes occur because of the plate tectonics. And I should tell you that, earthquake science is relatively young. It is not like physics, chemistry, mathematics. Earthquakes became a very serious topic of study only after about 1960s. And it is actually after the Second World War. So what happened was, like many things that we do today, like including your GPS, these are all American defense contributions. So after the Second World War, there was a Cold War. So people wanted to know whether anybody is using nuclear testing, nuclear blasting, etc. So the US defense installed instruments all over the globe, everywhere. Until then, earthquakes were just random, and they didn't understand why there is a pattern. Nobody knew. This pattern was not very clear. From 1964, they established a network called the National Earthquake, Worldwide Seismographic Network, which generated a lot of data. When they plotted the data, they knew that they are not just random. There is a pattern, And the subsequent lot of other work that was going on at that time, oil exploration, geophysical surveys, they produced a lot of data, and that is how the theory of plate tectonics originated in the late early 70s, mid 60s actually. The theory of plate tectonics was used to explain why earthquakes actually happen. So that is almost like, you know, in biology you have the theory of evolution. So in earth science, it is actually the plate tectonics that's the all-encompassing theory that explains earthquakes, volcanoes, climate change, evolution. There are lots of things that, you know, when I used to teach, I'll challenge my students, I'll say, everything that you see on the surface, including mountains, you know, evolution, isolation, like, you know, you have marsupials living only in Australia. So all of these are actually explained by plate tectonics. And if you find out something that is really not explained by plate tectonics, we can have a debate on that. Almost everything that you see on the surface of the earth, on the earth, it is explained by plate tectonics, including, like studying how the evolution happened, how migration occurred, how some people evolved separately, all of these things. So plate tectonics is fundamental to understanding the earth process. So why is there plate tectonics? So it is because if you look at the layering of the earth formed about 4.5 billion years ago. When the earth formed through the giant explosion, it was a boiling mass. Then later on with the time, it started differentiating, and denser material started sinking down, and lighter material started floating up. Then volcanism was there, meteoritic impacts were there. In the beginning, there was no water. Later on, because it was too hot, whatever water was there would evaporate. And then there were no land masses. Then slowly, with time, the land masses evolved, atmosphere evolved, and also the earth differentiated by forming the top layer is the crust, then there is a lithosphere, the whole thing. Then there is a mantle, and there is a core, inner core and outer core. And actually, inner core is actually solid and outer core is liquid. Now, what happens is there is a lot of radioactive material that is sitting within the core, which formed when the earth actually formed, and they are denser, so they started sinking deeper into the earth. And they produce heat because of the radioactive decay in a potassium becoming potassium, thorium, uranium. All of these are radioactive minerals, so they produce a lot of heat. And that heat travels up, and it starts bringing material, like, there's a lot of upwelling that it brings material up, and on the surface it will find a place where it will come out, and that's what you call the spreading center, and that's how you how you make the oceans. So if you look at Atlantic Ocean, 200 million years back, Atlantic Ocean was not there. The continents were together. So in between that, there was a mid-oceanic ridge through which materials start coming, and they start pushing the plates, and they will diverge, and that's what you call a spreading center, and that is where the new ocean will be formed. As the plates move, they will, like, you can look at the top thing, they will move and they'll collide with another continent, another plate, and then either if you collide with the continental plate, they will collide and become a mountain because both are the same density. If you collide with an oceanic plate, an ocean and continent, the oceanic plate being denser, it will subduct. So you will find subduction zones, that is where the denser plate is diving below the lighter plate, like Japan, Indonesia, Chile, all of these places, South American, all of these places are where oceanic plate, the Pacific plate is subducting beneath a continental plate. If you look at India, India collided with Eurasia. India is a continental plate, Eurasia is also a continental plate. So they collided, both are the same density, so they cannot dive each other. No one can dive, so it rises like a mountain. So you get collision zones where two plates collide and form a mountain. You get collision zones where denser material dives down and make a subduction zone. That's where you get tsunamigenic earthquakes. And you also have these spreading centers where the new things are formed and they start moving. And the movement is, it could be like a 2 centimeter. Indian plate is moving at 2 centimeter now. It used to be 5. Pacific plate is moving many places, it's almost 20 centimeters. So the plate is moving, and they, because of the movement, eventually it will collide here and there, and then once it collides, it is highly stressed. It cannot do anything else. So the rocks there will be highly stressed, weak, and it cannot accommodate any more of this push. But the push keeps on coming because the ocean is still growing. So that small component of stress is coming into the plate boundary, and that is when the rocks cannot take the stress anymore, it will break. So that is why the larger earthquakes occur along major plate boundaries. Is that clear so far? Okay, so this is the kind of the overall architecture where you have the heat coming from the inner core. It melts material, it rises up like we call a plume or something, then it comes to the mid-oceanic ridges, and then it starts pushing the plate starts moving, and eventually it collides. So it is believed that this kind of thing goes on around 200 million years. That is one cycle of movement. So the Himalaya is not going to sit there forever. Himalaya will move out from there, and it will also get eroded. Okay. So it will also get eroded, that all that height will go, and it will just leave a contact. Okay? And we will come to that because that's also important from earthquake point of view. Now you have to remember that that particular Himalaya is going to vanish in 200 million years, eroded, and then it will reach somewhere else. So like this, for the last almost 3 billion years, from the time the crust formed, from the time the continents formed, these continents were moving around on the globe. Okay? So if you go to Antarctica and if you make a deep hole, you will find forest, remnants of Carboniferous forest there, because Antarctica was, coal fields will be there. If you go to Greenland, you will find, below that you will find a forest, tropical forest will be there. So that means that the continents were wandering, always wandering around, moving around because of these forces. So today what you see is a current super cycle. This will change. And what I want to hint at is what Himalaya represents today. After 200 million years, they will fragment into smaller faults, and it will sit somewhere else. It is not Himalaya. It will be still a fault, but a dead fault. And that dead fault also can get activated once in a while. Okay, that's why it is important. Okay, so this is the overall architecture of how the subduction happens. That is where I'm not supposed to move from here. That's why I cannot go there. So you have that cone of red material that is actually coming out to the spreading ridge, and then it start moving. And you can see this is where it. See, this is that slab. This is a slab that is coming down. So you can have earthquakes till here, till the slab is cold, and then it melts, and then it moves. So so you have different type of boundaries, like I said. Spreading, that is where the new material is created. Collision, where continent and continent collides and become a mountain. And you have a denser material subducting beneath, where you have also the volcanoes. So you have the earthquakes and volcanoes. So now I come back to the plate boundaries. So these, if you remember that old picture, so these are the way the different plates are there. You have the Eurasian plate, African plate, South American plate, Indian, India, Australia plate. Actually, it's called the Indian plate, Australia together. So this is the way the plate architecture is there, and they keep moving. And one important thing in this whole architecture is what you call the ring of fire. Ring of fire is what covers the Peru, Chile trench all the way going up to the western part of North America, going through the Aleutian Trench in Alaska, all those places, coming back to Japan, then coming all the way to Indonesia. So this is the pocket, this is the stretch where you find the largest earthquakes in the world, tsunamis and volcanoes. So this is where the Pacific plate is subducting. So you can see the blue. The blue is actually the oceanic plate. The oceanic plate is subducting beneath all of those continents. So this is the famous ring of fire where you will find all the great earthquakes. Great meaning they are generally more than 9. We'll talk about that. So I want to just remind you once more before I close this aspect. You have the plate boundaries. Now you remember that. The middle of the ocean, you will see the very narrow, that is the spreading ridge. The spreading ridge earthquakes are not big. They are generally magnitude 4, 5 like that. And they will be shallow. Okay. So that is these patches. Okay, these are the spreading ridge patches, and then you can, they don't bother us because they are happening in the ocean. And then you will see the, all this continent, the yellow colors, basically they are, again you can see up to 700 kilometers it is going. So these are the subduction zones where you find deep earthquakes. Then you can see the only continent, you see the only continent where, continental region where a collision has occurred is here. See, that is where you will find all the, other than the ring of fire, that is where you will find the earthquakes occurring between the Indian plate and Eurasian plate, going all the way to the alpine belt. So it is basically the only place in the continental region where you get great earthquakes. All other places are basically plate boundaries where oceanic plate is subducting beneath a continental plate. Okay? So this is the most active intercontinental collision zone, the Himalaya. And you can see places like Australia, Eurasian plate interior, South America, western part, eastern part, North America, there are no earthquakes there. Only once in a while an earthquake will happen, but they are not densely packed with these red dots. Now I want to just mention a few things about the earthquakes, the parameters that we are actually seismologists are interested in. One is the epicenter. So I told you that we use seismograms to calculate the latitude and longitude of an earthquake, that is the epicenter. Then we want to estimate the focal depth. All this is done from the seismogram. Okay? So you have about, now you have a lot of data. When an earthquake occurs, you get a lot of seismograms. And we can use our programs and models to calculate the focal depth. Then what is the fault orientation? See, fault orientation is very important because very often you have to understand where this earthquake has happened. Is there a fault? Was there another earthquake? Sometimes the fault is not exposed. So you have to model the fault using the seismogram. And then the magnitude, which I will elaborate a little bit because that's something that is most confusing for everyone. So basically, we are using the seismograms to calculate the magnitude, focal depth, the location, etc. Faults are usually expressed in the field. Some are hidden. You'll have to infer it from the models. And for the expression of the fault is very important because how much is the slip occurring, what is the orientation, all this is actually very useful. Another parameter is the intensity. This is basically not measured instrumentally, but it is basically how it is felt. Like, intensity 1 is not felt, 2 is not felt, 3 will be mildly felt, and then, some clocks will hang, the hanging objects will fall, pictures will fall, like that. So you have to ask people how you felt it, or you look at buildings. There are new codes which will talk about how the structures, engineered structures have failed and all that. One important catch in this is, if you look at earthquakes which have happened long time back, like 200 years back, you think about an earthquake happening somewhere in outer part of Bangalore. Reporting will be mostly from Bangalore. The newspaper will say it was felt in Bangalore. The earthquake is not in Bangalore. So it has got a high bias because of the population. And if the earthquake has occurred in the ocean or in the forest, there is nobody. Only some people will feel it. So it depends on where you are. So it's a very tricky thing. The intensity is not a very believable thing. So whenever we have these intensity values for old earthquakes, one has to be biased. I will show you one example from Bangalore itself, that Karnataka, 2 earthquakes were reported from the same place, same date, same time, 2 earthquakes. So it's actually, people are reporting from Bangalore because the newspapers are, more active in an urban area, so they reported. So there is a little bit of bias in looking at old data. So just a pictorial representation of the things I mentioned, that the earthquakes originate at depth, that's called the hypocenter or a focus. The projection of that point to the surface is the epicenter, and you have the fault line that, you can see this fault is here. This is where the slip is occurring, and this is the whole area that is ruptured. So based on the size of that area, size of the fault, which means you have a larger fault, you will have a larger area and larger magnitude. You have a smaller fault, you will have a smaller area and smaller magnitude. And when you come to places like South India, like I mentioned about the Himalaya after 200 million, South Indian, where we are sitting, these are all like 2.3 billion years old. The rocks that we see around are 2.3 billion years old. So the faults that are formed over this period, some may be 500 million, some may be 200 million, we don't know. But they are all very small faults and they are unlikely to generate great earthquakes, not like the Himalaya. But faults will be there. For the reason I said, they are relics of some previous tectonics, millions of years old. So you will see a fault, it doesn't mean that it is going to create an earthquake. So when you see a fault map of Karnataka, you will see maps, I'll show you that. It doesn't mean that it will create an earthquake. Understood? Because this fault is old, it is dead, it is not active anymore. Okay? So what is a fault? A fault is when an actual earthquake happens, this is how the surface is looking like. One block has actually just slipped down. And if you cut that place, you will see places like this. You have a layer, you look at geologists, you look at this particular layer, you can see that this has moved up and this has moved down. In my book, I narrate a story from, there's a very famous seismologist, Caltech-based seismologist. He has written a book. That book is about earthquakes in California. So he talks about, I have used that anecdote in the book, that my book, our book in Penguin. So what they are saying is, you just look at this picture, and then I'll tell you that story. So that the book says a couple were actually doing hunting. They were hunting for elks in the morning in somewhere in Idaho. So it is a very misty morning, not very clear. So these people are sitting in a nicely, they are perched in some nice place, and they're looking at the elk, and then the crosswire is just balanced, ready to shoot. And just when they are ready to shoot, the elk vanishes from the line of sight. So it was an earthquake. So he says the earthquake actually saved the elk, because you can imagine the elk was standing on this fault, this block. The earthquake occurred, that block went down. Okay? So I use that anecdote in the book to say that what we see around today, around all these things that Earth is showing us, they are all creations. That is a moment in time. So an earthquake creating a fault and a morphology is only a small snapshot of time, as the Earth is still an evolving planet. It is still a planet in the working. It is still happening. So it is not dead. It's a very live planet, and that's why all these things are happening. Okay, so this is what a fault is. So we always look for this kind of faults. And if you have good exposures like this, we might find repeat events. You will find that this fault works again. So geologists know that this fault has moved 3 times, 4 times. So they know that earthquake is happening here. So if you go to some fault in Karnataka, they will show no sign of movement at all. That means it is dead. It is not moving. Okay. So these are some of the famous faults. The most famous fault that is exposed on the surface of the Earth is the San Andreas Fault. You can see on the western side, you can see that whole red line. It's actually a plate boundary between the North American plate and the Pacific plate, and it is defined by, it is not a subduction zone, it is not a collision zone, it is just a sliding zone. Okay? It is not diving. And you can see an earthquake occurred in 1906, so this is also an evidence of faulting. You can see this fence just moved like this, and you can see this stream just moved like this. So these are all morphological expressions, cultural expressions of fault. So I mentioned about seismic waves. So you have different types of waves, P waves and S waves. Then P waves are compressional, and they arrive first. Then comes the S wave. Then comes much later comes the surface wave. Later on, I will tell you why some people are able to do early warnings, because of the lag in the arrival times of these waves. Okay, we'll just touch on that. And earthquake magnitude. So we were talking about magnitudes. You have magnitude scale is, it was every time you hear about Richter scale. Richter scale is not an instrument. It is just a formula that calculates based on the amplitude of the seismic wave. They calculate the magnitude. It is a California-based scale, and it's a log scale. So one point represents a 10-fold increase in size. So magnitude 4 to 5 is actually 10 times larger, and the energy release is about 32 times from one scale to the other. Okay, and major earthquakes like 1960 Chile earthquake is the largest recorded earthquake. It is 9.5. the largest recorded in the history. It released an equivalent of 550 million times the energy released by the Hiroshima atomic bomb. So this is the kind of energy. So you have magnitude going up to 8 and 9. There is no close. There is no maximum or minimum. It is an open-ended scale. But the maximum what we have known is 9.5. But when it happens, the instruments also get clipped. It doesn't record the waves. It will get clipped. But these days you have digital. And then you have another way of expressing the size of the earthquake is the intensity. For old earthquakes like 1934 Bihar earthquake, the instrumentation is very poor. So what we work on this is how to calculate the intensity. So because Bihar plains at that time is highly populated, so people go around and do geological survey of India and all that, and they will calculate what was the intensity and make a map which is called an isoseismal map, and then based on that they will find out what is the epicenter, because there is no instrumental data. And these days, there are also computer programs that will calculate an earthquake occurs. Immediately, they'll tell you what is the shaking effect, how much shaking will happen, what is the maximum distance it will cover, etc. So that's called a shake map. So the shake map is useful for people to understand what kind of buildings are going to be affected, etc. So we talked about the movement of India. So Indian subcontinent was sitting somewhere south of current equator. You can see that equator, blue line is there. So India was far away from equator at that time. So around 71 million years onwards, they have traced the, you know how they find this out? So what they do is, there is some, if there are physics students out here, then they would know there is something called magnetism, right? So what happens is the earth keeps changing its magnetic field once in a while, like they reverse the magnetic field, its orientations change. So every time I told you about that mid-oceanic ridge is producing the material and it is getting solidified, it will magnetize in the field that is available at that time. Okay, magnetic field keep on changing. So it will use that kind of data to calculate where a particular patch of continent was. Okay, it is still moving. So during this 70 million, the magnetic field has changed and the poles have changed. So you have the magnetic pole which is almost close to the geographic pole. So they will calculate. That is called the study of paleomagnetism. So that's what they use, plus a lot of other data. So they will calculate how the Indian plate has moved, and about 40 million years ago, it just collided. It collided with the Eurasia, and then you formed the Himalaya, this boundary. Okay, India is still moving at about 2 to 3 centimeters per year, and you formed this collision zone, which is the Himalaya, and then you find this subduction zone because this is an oceanic plate. So you will find a collision zone mountain and you will find a subduction zone. Incidentally, there is one volcano in the Indian subcontinent. Anybody knows where it is? Can you make a guess at least? One volcano. No. It is in Barren Island. It is in somewhere here. So that's a part of the Andaman group of islands. So you can have, so that is actually a subduction zone. But it is not a very live, not very active volcano. During 2004, it exploded. After the earthquake, there was some movement of magma and all, it exploded. We used to have a GPS station there, it got thrown off in the earthquake, and then we lost it. So this is how the tectonics is, and that is why now you can remember the map of earthquakes. That will show you that is the boundary along which you will find all these earthquakes. So the boundary defines the pink dots, lot of earthquakes, and if you come, and now you can ask me, why do earthquakes happen away from the plate boundary? Now the plate is moving. I told you there are relics of old faults out there. The stress is still there. So once in a while, some of those faults which are not very prominent, not like Himalaya, they will give an earthquake. So suddenly you will find an earthquake in Killari or other interior part of India. But you can clearly see that they are magnitude at the most 6. So we have had magnitude 3 or 3 earthquakes of magnitude 6 in the continental. So we call them the continental stable continental earthquakes. So what is the characteristic of stable continental earthquake? They occur away from the plate boundary. They are generally smaller, moderate, like magnitude 6 or 6.5, and they are shallower because they are not part of the subduction zone. So they can be very damaging, and they occur very sparsely over long intervals of time. So therefore, they would look as if it is a bolt from the sky. You don't have any idea earthquake will happen here, and it still happens. So it is a unexpected thing, and it happens in the most unprepared area because they are not expecting an earthquake. So that is how these earthquakes happen. So you can see based on the history, the Bureau of Indian Standards has made a seismic zonation map. So after the Killari earthquake, they have moved the zone 1. See, before that there was a zone 1. Zone 1 was ideally where an earthquake, no earthquake will happen, okay, zone 1. And that was where Killari earthquake happened, which tells you that there are a lot of things which we don't know. We base that map based on our experience maybe for the last 50, 60 years. But the earthquake must have happened 15,000 years ago, and it repeats 15,000 years later. So we don't know. So the zonation map was upgraded. Karnataka is still in zone 2, and part of that, that light pink, that slightly darker pink on the coastal area, that is actually zone 3. Zone 3 implies that maximum can be magnitude 6, 6.5, intensity about 7. So that is a zone 3. But if you go up, you can see all the Northeast India, Himalaya, Kashmir, all of those places are red, and they are more prone for earthquakes. So what you see on the left is again just the patch of earthquakes on India. So now I will just show you. See, if you go and find all the historical earthquakes, you will find that there are few earthquakes also in the South India. Like one is this Koina earthquake of 1967, which is associated with the Shivaji Sagar Lake. That's another animal, like how you generate earthquakes by filling large reservoirs. Then you have the Killari earthquake, which was very damaging. Then you had Jabalpur earthquake, you have Kutch earthquake. So you can see once in a while you do have, and then sometimes you also have misinterpretation. The 1341 is actually a flood, but people have put it as an earthquake, but we have later on investigated it. It's actually a flood. Similarly, the 1618 in Bombay, that's also like some kind of a storm or something. It is not an earthquake. So so this is why I told you we have to look at the historical data very carefully before we can, and then you have the Himalayan earthquakes. Now, if you look at this map, now this is the stable continental earthquakes. You will see that very few earthquakes are there, and they are mostly magnitude 6. You can see the Australian continent, you have some, here you have some, and then some here, nothing here. So, you have that very few earthquakes. And I put that map to the left to show you that there are old structures, like Narmada, what you call it, it's a rifted zone. It's a fault structure which is very, very old, 500 million years, but they also produce small earthquakes because they are faults anyway. They are not very active. So you will find Godavari Rift, Narmada Rift, these are all old rifted structures. So that is where the earthquakes are actually happening. This is just to remind you that same thing, like you have different, during the movement of the continent, old structures also are there, and they get reactivated, they get activated, and they will produce earthquakes, but not more than 6.5, okay? So we really don't have to worry. So here is the Killari earthquake. The Killari was very damaging because, people were not, you can see these buildings. See, they don't use any kind of concrete or steel or anything. They are just using the building, the basaltic rocks from the local area. They'll use the same basaltic soil as a plaster, and they just build it. There's no iron or no roofing, no lintel, nothing. So they just collapse. So that is how the damage was very large, and the whole village of Killari got totally destroyed. But this was a very interesting earthquake because it produced a small scarp. So usually I told you the fault. The fault has not appeared on the surface, but it just produced a small projection. It was just about 80 centimeters, and it was a broken patch of about 2 kilometers long. So when you get such things, the good thing is you can go and investigate that area. Otherwise, it's a barren land. You can see it's a no features, it's a flat land. So you can go and investigate in that area and find out if of previous faulting has occurred there. Okay? So, that is the advantage of this kind of structures, which is what we did actually. We did excavate. You can see there is a very subtle fault out here. There is a movement, and that was dated to be about 17,000 years. So, which means that earthquakes in places like Killari are very rare. They occur only once in 15,000 years. So, we do not expect an earthquake to happen there. So, there is no preparation. But when you look at the historical earthquakes, you will see when an earthquake happens, people go and dig up all information and find out what has happened. So, they will find there were actually few earthquakes, and they follow some trend also, but they are all magnitude, intensity 4, 5, nothing big. So, we understood that the earthquake is very shallow, and that is why there was damage, plus the lack of preparation, and also earthquake occurred in the morning like 3:30 when people were all sleeping. So, the damage was very, very large. So, I told you about my most fascinating place, which is called the Run of Kutch, where we had this magnitude 7.8 earthquake. What actually happened there, I told you there was, people went to sleep. In the night, this earthquake occurred, and when they woke up in the morning, they found a new lake was formed. That was this lake. So, that lake is still there. So, because the land came up for about 3 meters high, and it blocked a tributary of the Indus River, and it created a dam. So, because it was not there when people went to sleep, they said this is a miracle by the God. So, they called it the Allah Band. It was created by the God. So, we wanted to investigate that, and no one actually had gone there. No one knew what was the actual height of that, except some millimeter surveys were there. So, over the years, it has been eroded. This is a part of that. Here also you can see a small part. We went there in 2018 with some students. That's the two of us. So, this part is a part of that. Here, this is eroded. So, over the years, this gets. So, what we were doing is we wanted to excavate this some places and look for the past earthquake. So, that was our mission here. So, that is why it becomes very mysterious, and you go to these places, there will be some local people who will come and watch what you are doing, and then we are cutting into area where there is a historical settlement. We are actually in the Indus Valley, part of that civilization. So, when you make trenches, you will find some small Kangan and things like that. So, these people would say that these people, how can you find earthquakes by digging this place? They are just looking for some, nidhis there, some gold or something they must be looking for, So, otherwise it is good for second place, you dig up one day, come back next day, everything is covered because of the salt, because the wind carries a lot of salt. And it's a very difficult place, but so fascinating. I can never say no to this place. So, this was in 2018 we went back, because that was the 100th year of that earthquake. So, we took a lot of students there, and so this was the lake was. So, this is why it is very important, and we wanted to find out when was the last earthquake. So, what did we do? And it is very fascinating, See, this map is prepared in 2000, this was prepared in 1907. And you can see that there is an inlet, the boats used to come, and today that one that is below is today. So, just imagine how the morphology has changed in about 1,000 years. The whole landscape has changed. So, we went to these places because we wanted to find out when was the last earthquake. So, what do we do here? So, during a great earthquake, something happens. In these kind of places where there is water table, there is something called liquefaction. So, what happens is mud and water and everything just comes out, they get ejected, and they will come to the surface, and they call them sand blows, and they remain there. So, these can be preserved. So, what we are looking is, we go there to look for old sand blows. So, what could happen is sometimes some things will fall into these pits, into these holes, like maybe a bone, maybe a twig. So, we can date them and find out what is the date when it formed. Okay? So, we have to find out where to look for. So, we would trench, and so here you can see there was a fort, and that fort, that is like a collection center, that had fallen. So, what we thought is, if we go and dig up that same place, if there was a fort in the past, we would find the remnants of that. So, that's exactly what we found. So this was an old liquefaction feature, and here you will find traces of bricks with charcoal. So this was dated to be about 1000 years. So we found the past earthquake, which was, you can see this also, the dike is coming. So here is the horizon, a settlement horizon with bricks, and the sand dike is coming up. So these are not there for you to just pick up. It takes a lot of work to find out where you should expect this, and a lot of frustrating digging, and finally you will find it. And when you find it, you must also find something datable, like it could be like a bone or a charcoal or a brick or something. So here we dated this earthquake as 1000 years. And then there were some historical anecdotes. Okay, I'll just quickly move into the Himalaya. Just only a few things I want to tell about Himalaya. In Himalaya, the problem is we have had several earthquakes like 1950, 1897, 1934, then 1905. But there is a patch here between 1934 and this one, 1905. There is a large area which has not generated a great earthquake. All other things are great. Okay, magnitude 8, 1897, 1934, 1905, 1950. All these are magnitude 8. So in between there is a patch. So this is expected to generate a great earthquake in the near future. So that's why it is called a gap in activity. So we started working in that area. I want to mention this because of a particular technique we used. So I said about geological data. Now there are also historical data. So in Himalaya you have a lot of temples. Himalaya is an active place. You have temple history going back to about 1200 years. So you can use these other cultural structures to understand whether there is any earthquake related damage on that. And Garhwal region is famous for temples. So we looked at many temples. So you can see this is the Vamadev temple, which has it has rotated. But here also you have to be very careful. Like if you go to some temples in Karnataka, there might be some vandalism related damage. So you have to distinguish between an earthquake related damage and a vandalism related damage, or just an age thing. So you have to connect it with a lot of information to be able to say that this was indeed due by an earthquake. So look at this very famous structure, Qutub Minar. So you can see there is this construction style changes from here. You can see white marble coming up there. So here this is, like I said, this is like a Sherlock Holmes business, because you have to observe small things, and you have to go back and read the literature. So what happened is there was an earthquake there was a reconstruction in 1368. See, that is the patch. Okay, but there was an earthquake in 1330. So you look at the literature, you go to the archives. So we have people working with us like archaeologists, historians. So you have to understand these things become like a index to understand that okay, something has happened. So that actually, what does it tell you? It tells you that after this, nothing has happened. Okay. So it tells you that after this there is no damage has happened here, which means that no earthquake has happened at least for the last 600 years. And then the models come. The plate is moving, all these models will come. That is why they say 600 years this particular segment has not generated any earthquake, therefore it is ready. It is ready for an earthquake anytime. So what is the advantage of that? It will tell people that, okay, when you are doing your dams, when you are doing your metros, of course nobody listens to all this, that you have to be prepared for that shaking. So the next step is, if an earthquake of magnitude 8 occurs here next year, what is the expected ground shaking in Delhi, and how your structure should be designed so that that shaking can be addressed. So that's the advantage of this kind of studies. So the tsunami I just mentioned very briefly. So these are the tsunami patches. We have had tsunamis. These are remember the ring of fire. So it is just basically the ring of fire. Okay. So that is where you will find all these earthquakes. Why tsunami happened? Because of the plate is subducting. You know that now. Earthquake happened. Your question, why they are happening deeper? You have deeper here. It will still go deeper. And earthquake occur right on the ocean floor. And the displacement of water will happen, and as they travel towards the shore, the waves will assume a high elevation, and the waves will come to the shore. So during this earthquake, a lot of things happened, like land came up. This is Sentinel Island, this is Port Blair. So we use these also to understand the past earthquake. Like here, there is one my student did. So this is like that is before the earthquake. The Indira Point, the southernmost point of Indian territory. It was 3 meters. It just land went down by 3 meters. So here the land went up by 1 meter. So these are the barnacles and all which live on the the mangroves. They die because they got elevated above the water level. So we use all these to use along with the. Here is one spectacular case where that's one of my students. She did a PhD on this. So what she was doing is the land, actually I showed you the land subsided. But when there was a low tide, we could see this line of tree roots exposed. But we dated that and found to be about 700 years. And through several other data, we could prove that, including data from Tamil Nadu coast, we could prove that the last tsunami was about 1,000 years old. Okay? So these are the kind of things we just quickly go through the earthquake history of Karnataka. Karnataka has had some earthquakes like magnitude 5.2 all the way back, in like 22 years back, 36. This is the recent data. There's one more data that I'll show you. So you will find generally only this earthquake of magnitude 6.6. So these are all the Killari earthquake. It's not part of Karnataka. Then you have the Koina earthquake. These are otherwise you will find only magnitude 5-ish, 4. So this is another map that data collected from the national. You can see that you find also earthquakes in the ocean, but not many. South India doesn't have so many earthquakes. So this is a table that I put together. It starts with 1505 in Belancourt. Then there is a Bijapur. And you will find, see, this is what I was telling, that same event will be near Bangalore, same event will be reported 2 times. So like this, you will have a lot of data. The largest one is actually Coimbatore, 1900. And Bangalore, we have had some, you can see some small patches here. This is Bangalore here. Some small patches will be here, but these are all magnitude 4, occasionally 4, like that. So it is nothing very serious. So I showed you that the faults, some people have used to show the fault maps of, but you don't see any earthquakes near the faults. Those red patches are the faults. And I want to point out one event where a lot of earthquakes, small earthquake happened, and it was actually triggered by rain. That was the understanding. So they identified these 3 clusters. Some people actually worked on it. So they were doing all these studies, and they were showing that it is actually related to rain. So what they're plotting is the wavy patches is rainfall, and the green bar is the earthquake. It is highly contested. We are not really sure, but there is a mechanism by which rain can trigger earthquakes. That is because of the water infiltrating into the subsurface, because of the changes in the land use pattern, the infiltration pattern. The pore pressure can increase and it can weaken the fault. So it is a possible mechanism, but they don't create big earthquakes. You must know that water happening, water filtrating down, these are all very shallow processes. And you have to go back and remember that shallow means small earthquake, small fault. So you will suddenly find a cluster of earthquake happening, they call it a swarm. It could be related to a rainfall, because remember, you have also changed the surface properties. The infiltration of water is changing, the surface runoff is changing. So you can, this is what you call a hydroseismicity, the earthquake triggered by water. Okay, so we come to the end of the topic. So I like this quote. I think I used it in my book also. There are a lot of things we don't know about the earth processes. So this is a very famous quote by US Defense Secretary Donald Rumsfeld. He was talking, he made the statement in a news briefing after he looked for evidence Iraq with weapons of mass destruction. What did he say? He said, read it carefully, there are known knowns. Okay? We know certain things exist. There are things we know and we know them. We also know there are known unknowns. There are many things we know that they are unknown. That is to say that we know there are some things There are some things we do not know. There are also unknown unknowns, the one that we don't even know that we don't know. So that is the kind of thing that happens when a tsunami hits you, that we never knew that a tsunami could hit the Indian shore. So this is true for the earthquake prediction. Like, can you really, why are they so difficult to predict? It is because the simple answer is there are too many unknowns. And also, unlike volcanic eruption or weather, landslide, the processes leading to an earthquake all happening beyond our realm of observation. We cannot observe anything. We have only indirect, not like weather, you can measure, volcano you can measure how it is bulging and you can predict. So you cannot predict all these things, and there is no pattern. Some earthquakes will come after foreshocks, some will come just like that. All kind of difficulties are there. So that is why in a recent article in Nature Communication, they titled it as why can't we predict earthquakes? We can't predict earthquakes. So they say that it is almost foreseeable future. They do not see that we can actually predict. So what can be done? Like I mentioned, we can actually understand where earthquakes can happen, what could be the size of the fault, because of the size of the fault, what could be the damage, because of the potential depth, what could be the damage, and then you can understand, you can predict the effect of that earthquake. You can predict that if an earthquake happens in Himalaya, we know that it will happen. It's only a question of time. What will happen in Delhi? So you can only make scenarios and then be prepared. Okay? Most of what I said, these are two of our books. This one is a popular book. The Rumbling Earth is a popular book which is meant for common readers. The other one is a technical book. So this is what I wanted to share with you. Any questions? I'm happy to answer.